Hello everybody. So in this video we are going to solve one example on the pipe networks. This is going to be a very simple example, and my goal here is to show how we can deal with such kind of problems and to see the equations that we use. If you remember last video, we agreed on the on the rules that we are going to follow to solve pipe network problems, and we said that it's going to be mainly the conservation of mass, which is the mass at any node, which whether it's splitting point or merging point, it's going to be in equals out, and that the pressure drop for any two junctions parallel to each other must be equal. Okay, or the head losses, yeah, both are the same. So this is what we have here. So we have two tanks where there is a pump that is used to pump there are two tanks filled with water. There are two pumps that there's a pump, I'm sorry, that is used to pump the water from the smaller or the first tank to the second one. And the elevation of or the surface water of water of tank A, which is point A, is 5 meters, and for tank B is 13 meters. And the length of the pipe, the two pipes have the same length, which is 36 meters. And the two pipes are made of commercial steel, and the diameters are 4 meter and 8 meters, and water is to pumped by a 70% efficient motor pump. So this pump has an efficiency of 70%, and the electric power is 8 kilowatts. The minor losses and the head losses in the pipe that connect the parallel pipes to the reservoir are considered to be negligible. So the minor losses due to these elbows is going to be negligible, and the loss in this part and in this part, the inlet and exit, of course, of the pipe are going to be negligible, in addition to the losses in these short connections before and after the branches. We want to find the total flow rate and the flow rate in each of the two parallel lines. So the total flow rate and the flow rate for each one of these two branches. So these are the givens. I just put them in the SI units, and this is the difference in elevation. It's going to be 8 meters, and here is the commercial steel pipe. So epsilon is 4.5 times 10 power minus 5 meters, and we know the electric power is 8,000 watts, and the efficiency is 0.7 or 70%. So from this we can find the mechanical work, which is going to be the efficiency times the electric work, which is 5,600 watts. And from this we know that the power is mg h pump, so or rho gv h pump. So from this we can find the relation between the pump head and the volumetric flow rate, which we don't know. We don't know this volumetric flow rate. So this is the pump head, and now we can apply Bernoulli equation between points A and B, and from Bernoulli equation we know that the two tanks are open to the atmosphere, so the two pressures are equal. We know that there are two big tanks, so the velocity of the surface is going to be very, very small, so we will consider it to be 0. We know the difference in elevation. There is no turbine, so there will be only the pump head is equal to difference in elevation plus H losses. So we know the pump head already, and we know the difference in elevation. So from this we can find out that the H pump, which is 0.571 over V dot minus H losses, is equal to 8. Okay, so this is the equation, the first equation we got, which is the relation between the head losses and the volumetric flow rate from Bernoulli equation. Now we have we can apply the rules that we just discussed before. So we have the mass balance at the splitting junction or at the merging junction, which is the total volumetric flow rate. Of course, it's incompressible fluid, so it's going to be the total mass in, or the volume, the mass flow rate in is equal to mass in branch 1 plus mass flow rate in branch 2. Or we can put it as volumetric flow rate because it's an incompressible fluid. So we have another relation here, which is the relation between the volumetric flow rate, the total volumetric flow rate, and the two volumetric flow rates. We also know that the two branches are in parallel, so the losses in branch 1 is equal to the losses in branch 2. Now we want to find the losses in each one of them. So the losses is, as we know from Darcy's equation, it's FL over D times U square over 2G. And I put the subscript 1 here to differentiate between the first and the second branch. And we can put the velocity as the volumetric flow rate over area, which is pi over 4 D1 square. And from this we have D square power 2 and D power 1, so it's going to be D power 5. So this is now in terms of volumetric flow rate and D power 5. And we also can write Reynolds number in terms of volumetric flow rate and the diameter. So I'm trying to put everything now in terms of volumetric flow rate so we can unify the variables that we have in all the equations that we are going to use. And we will see shortly why we are doing this. So I'm not calculating any numbers now. I'm just putting the equations in terms of the parameters or the same parameters. So now we have the Reynolds number is put in terms of the volumetric flow rate and the fluid properties and the diameter of the pipe. And now we have also the relation that we need for the friction. So this is all to get F1, and this is the relation that we need for the friction factor. And we know epsilon over D1, it's already given, so we can write the equation like this. Okay, so now we substituted with Reynolds number here, which is this number, and because we already calculated the Reynolds number from this relation, so we have the Reynolds number as a function of V1, V dot 1, and epsilon over D is already known, so it's divided 3 over 7 will be this number, and we can put HL. In HL we know everything except the volumetric flow rate and F1. So now we are putting the HL1 in terms of F and V1. Of course, this is F1 and V1 power 2. So this is the set of equations we have for the first branch. We can do the same for the second branch. So we can calculate the same 3 parameters: Reynolds number, the equation for friction factor, and the losses. So we have now a lot of equations. So to summarize everything, we have 7 equations. This is the friction losses for the first pipe, the losses, the friction factor for the first pipe, the losses of the first pipe, the mass balance on the splitting node, the friction factor for the second pipe, the losses in the second pipe, the relation between the two losses in two parallel branches, that is equal losses, and Bernoulli equation. So if you look at this equation, you'll see we have 7 equations and 7 unknowns. We have 2 friction factors, 2 head losses, and 3 volumetric flow rates. And to be able to solve this this set of equations, it's actually very hard because 7 equations, 7 unknowns. I tried to solve them using Microsoft Excel, but I failed. It didn't work. Then I tried more powerful software, so I tried this using MATLAB. And what you see here is the code that I put to wrote to define the 7 equations. So I have here a function where I called it the pipe networks, and the way it works in MATLAB that you have to name them all as x1, x2, x3, and x7. So I wrote this note here for myself to know that x1 is f1, x2 is f2, x3 is v1, and x4 is v2, x5 is v total, and 6 and 7 are hl1 and hl2. I wrote this equation so they are all equal to 0. So this is the I just rearranged the equation to be equal to 0. So I put all the equations here, and now in the command window I will these equations cannot be solved analytically. I cannot substitute one in another to solve the equation, so I have to solve them numerically. So to do this, we start with initial values, and we ask the software to solve this equation using the given initial values. So here I wrote here the initial values, which are I put for the friction factors initial factor of 0.2, and of course it's very important to have reasonable friction factors, initial values. So I know the friction factor has a range of 10 power minus 4 to 10 power minus 1. So I put it to be 10 power minus 2 to be easy to reach the final answer. quickly. And the volumetric flow rates are usually in the value of 10 power minus 3. This is usually the values in meter cubes per second. And here are the two losses. I started with 10 meters. I don't know, but it seemed to be like a reasonable number for me. So these are the initial values, and then I recall the function that solves the equation, which is called fsolve. And this is, I call the file, which is named pipe network, and then the initial is the initial values that it needs to start the iteration. So MATLAB is a very powerful software. So you see, it didn't take any time. It just said the equation is solved, and here we have the results. It says 0.0221, which is the friction factor 1, 0.0182, the second friction factor, 0.042, which is the first volumetric flow rate, the 0.0258, which is the second volumetric flow rate, and this is 0.03, which is the total volumetric flow rate, which is the summation of these two. And then the two head losses, which are equal, and this is the second output. Here is the error, or the difference from 0 that I want to achieve, and you see it's 10 power minus 13. So it's very good results. So now we have the outputs with accuracy of 12 zeros, which is very good. So it's very nice results that we got. So finally, these are the results that we have, and now we have the volumetric flow rates. We know the head losses, and we know everything about the two pipes. So I just want to remind you that this was a very simple example. If we have more branches, or if we have branches in parallel and in series in the same problem, it would be even more and more complicated, and we might have like 10 or 15 equations and 15 unknowns. So, and I hope this equation clarifies how to deal with these kind of problems. And we'll see you next video, inshallah. Goodbye.